Assalamualaikum. Very good morning.
Good morning, doctor.
Okay. Hope all of you are well today. Yeah, doing well today. So we're going to continue with our lecture 7. Okay. Yesterday we have learned up to the third type of Fourier series, which is a complex exponential type of Fourier series. Can you hear me clearly? Puan Jun Chen?
Yes, doctor. Yes, doctor.
Okay, so you can hear me, yeah? Okay, because I received a chat from Puan Jun Chen. He can't hear me clearly. Your volume too small, am I? It's too small. Is it okay then? I have to speak louder, is it?
I guess, doctor, it's okay for me.
Okay, all right. Okay, so hopefully uh, we can now start the lectures on these topics of Fourier series, the third type of Fourier series. Okay, so we have learned this basically the topics, the complex exponential type of Fourier series. Okay, we have learned about this VT, yeah, in which in a complex exponential form, the VT is written to be this form, yeah, summation of n from negative infinite to positive infinite of Cn, exponential j and omega naught t, where Cn is written to be this term, yeah, integration Vt exponential j negative j and omega naught t dt. Okay, so we did this example yesterday, and I hope that you have now understand about this construction, yeah, or illustration of a double-sided spectrum, which is for the complex type, a complex exponential type of Fourier series. Let's have a look at this example now, which is we are given a periodic signal of ft. Ft is equals to modulus of sine t with a period of t naught equals to pi. So we have to determine the function, the function above, or whether it is a type of odd, even, skew function, or a combination of the functions. That's the first question. Yeah, we have to determine the characteristics of ft given. And number two, you have to determine the ft in the trigonometric cosine form of Fourier series up to third harmonic with the assistance of the Fourier coefficient table. Okay, so we have to use the Fourier coefficient table to this particular function ft. Then we need to obtain its ft, its trigonometric cosine form of Fourier series up to the third harmonics. Yeah, so hopefully you're clear about the question. Right, so ft equal to sine t. Ft equal to sine t is basically a modulus of sine t, yeah, modulus of sine t. So we know that sine t is having a positive peak and negative peak. So when we have modulus sign for the sine t, it shows that all the negative peak will now reflect to the positive side. Yeah. So we're going to have all the peak will be at the positive side. Yeah, all the peak will be at the positive side. So basically, if we face this kind of signal where we have a sine wave, but the negative peak or negative value is said to be reflected to the positive side, we can see that all the sine curve will be on the positive axis or positive y-axis. Yeah, positive y-axis. So based on that, what type of function should it be? Should it be even function or should it be odd functions? Anyone? For the sine t function, sine t modulus.
I think it's an odd, an even function, doctor.
Good. It should be an even function. So let's have a look at the solution for this. Yeah. Okay. this is the one, sine t functions. Okay, so basically, the sine t functions with the given period of t naught equals to pi. So if we illustrate the ft function, it should look like this, right? So when we have this type of functions with the amplitude of 1, yeah, so what I meant just now is that all the negative peak, supposedly if it's normal sine t, we're going to have a peak up to 1, then it goes down to -1, and goes up back to positive and so on. But since you have a modulus, so all negative peak will be reflected to positive. So we're going to have a sine t modulus which should be look like this, yeah? And t naught pi, so t naught should be there because the signal will repeat for every pi value. All right. Okay, so that should be your sine t modulus, yeah? So we know that this should be an even functions clearly, yeah? Okay, so let's go back to the questions. We need to obtain by okay, we need to actually use a table. Yeah, we need to use a table of a Fourier coefficients table that I gave you in the attachment in the Google Classroom. Because from the table, we are going to learn how to extract the Fourier coefficients. Yeah. Okay. So let's have a look at this table. Sorry. Okay, this is the one. Table B3, yeah. So this is in the Fourier series attachment I gave you to you in the classroom attachment. Okay, the first page is all the formulations related to what we have learned yesterday. Okay, this is the first type of Fourier series, the second type of trigonometric, and it's third type, which is a complex exponential. Okay, and then we have a table B2, which we're going to learn today. Okay, and then this is table that I mentioned to you where we have the Fourier coefficients for this waveform. So we are given 7 type of waveform. So we have a square wave, we have a sawtooth, triangular wave, and so on up to impulse train functions. So for each given functions, we are given its respective Fourier coefficients, the C0 and the Cn. Yeah, C0 and the Cn. Where C0 basically is the value of Cn for n equals to 0, and for the rest should be the Cn. Okay, I repeat again. The C0 here is the value of Cn for n equals to 0. Okay, and the rest of Cn should be here. So when we refer to these particular signals of ft, so it can be related to signal number 4. Yeah, signal number 4, which is a full wave rectified signal. Okay, we can relate that question with this signal number 4, where for signal number 4, the amplitude is given to be x0, the period is t0. So if we are facing this kind of signal, so its respective Fourier coefficients should be given by these two. This is your C0. Okay, C0 equals to 2x0 over pi. X0 is the amplitude. Whereas for the Cn, it should be equals to -2x0 divided by pi of 4n squared minus 1. So this is the Cn. Rest of Cn apart from n equals to 0, because for Z0 should be here, yeah? Right, so we're going to use these two informations. We're going to extract these two informations to be used in calculating or in writing these Fourier series coefficients for the sine t modulus. Yeah. Okay, we go back to the solutions here. Okay, so this is what we have obtained. We have extract this from the table just now, right? So we have the C0 and the Cn, and from this Ft, we can see that x0, which is the amplitude, equals to 1. Okay, and the period of Ft equals to pi. The T0 equals to pi. So we're going to substitute both parameters here into these equations, and we go back to the fundamental equations for Fourier series of complex exponential type, where Ft is summation of n from negative infinite to positive infinite of Cn exponential j n omega t, and this can be further written to be this equation where we have a C0 Yeah, C naught is taken out from these terms, and we're going to have summation of n from negative infinite to positive infinite and not equals to 0 for this Cn, in which we have substitute omega to be equals to 2 pi over T naught. Yeah, omega equals to 2 pi over T naught. Okay, so from here, we can then use C naught terms, Cn terms, and these two parameters value, x naught and T naught, into these equations of ft, and we can write the ft up to third harmonics as requested from the question, up to third harmonics, in which it should be up to n equals to 3, yeah? N equals to 3, which is from negative 3, negative 2, negative 1, okay, we have 0, and then we proceed further with n equals to 1, n equals to 2, n equals to 3. Okay, so by this, you're going to have these equations of ft to be equals to, this is your C naught. Okay, we have a C naught here, which is 2x naught over pi. We know that x naught equals to 1, so you're going to have 2 over pi for the C naught. And for the n equals to negative 3, we have C negative 3 exponential negative j6 of t. Okay, because we have n equals to negative 3, T naught equals to pi, so we have 2, so 2 times negative 3 is negative 6, and it follows with n of negative 2, n of negative 1, okay, n of 1, n of 2, and n of 3. Okay, hopefully you understand about this. Any questions so far? Hopefully no, yeah? Okay, so we have write the ft in this form, and then we have to substitute the Cn here into all the C negative 3 up to C positive 3. So you're going to have these terms here. Okay, 2 over pi, that should be your C negative 3, C negative 2, C negative 1, and follows up to C of 3. Okay, in which all of these value for the Cn is obtained from these terms by substituting x naught equals to 1. Yeah, so you can work on that. So that should be your ft, which has been written in terms of complex exponential. So the purpose of this example is basically we want you to understand how to extract the Fourier coefficients value from the table.
Doctor,
Yes.
can you go up a bit? I have a small question.
All right.
So now above the x not thing. Yes. You see Cn equal negative 2x xo.
Okay.
How did we get that xo equal to 1?
It's based
Didn't understand.
on this diagram here. Okay, we compare this table, I mean this diagram given from the question with this attachment here, number 4, where the peak is given to be x naught, right? The peak is x
So it's
naught.
fixed. Yeah, it's fixed.
So it's x naught is the peak. So we compare this diagram in table B3, the question that we have here. So basically your x naught, which is the amplitude, shall be equals to 1, and the period of t naught, sorry, the t naught here shall be equals to pi. Okay, so we have to compare. So that's what I mentioned to you just now. You have to understand how to extract information from the table, yeah, to be applied in your solutions, yeah. Okay, so hopefully you understand now on how to apply.
Yes, thank you, Doctor.
Back, it's okay. Okay, but you have to be very careful on certain table, I mean certain function. For instance, if you refer to table B3, for example, signal number 1, the square wave functions, we can see that for this particular square wave functions, the C naught will be equal to 0. And the Cn is here, but you have to remember that there is another additional things here, that the Cn that we are having here will be equals to 0 for the value of even n. Okay, means that this value of Cn is valid only for odd value of n. Negative 3, negative 1, positive 1, and positive 3. Where for the n even, 2, 4, 6, and so on, the value will be 0. So you have to be very careful, yeah, on this additional comments for each table.
Doctor, even you mean even numbers, like 2,
Correct.
4?
Correct, because this is for an even, right? So if you have C2,
Okay, when it's
C4,
odd, what will be the comment?
okay, for the odd means that for this particular example number 1, the Cn that we have here is valid only for odd end. Yeah, for odd end. Okay. And the same things happen for these triangular functions here. Again, the C0 is given, the Cn is given, but there's a comment here that the Cn that you're having here is only for odd value of n, because for the n which is even, the value of the Cn will be 0. Okay, so you have to be very careful on writing this Fourier series coefficients for these given signals. Yeah, so you, right, hopefully you understand about this. Okay, so let's proceed with this example. Okay, so hopefully you're clear about these examples. Yeah. Okay, I don't want to proceed with this. Okay. Okay, let's have a look at these examples here. We are given the ft, which is equals to 2 over pi, negative 2 over 3 pi, exponential j of 2t, negative of 2, 3 pi, exponential negative j 2t up to these terms here. So from these questions, okay, from these questions, you have to actually predict what kind of waveform is this, yeah, given by these ft functions, and you need to sketch the waveform of ft. Okay, so you need to refer to the Fourier coefficients table. So from the table, we need to predict what kind of ft, what kind of function should be the ft, and then sketch the ft. Yeah, so let's have a look at the solution to this. Okay, so we have these solutions. Yeah, we have the given ft here. So I put here that the ft function is related to signal number 5. Yeah, signal number 5. Why signal number 5? Let's have a look at these terms here. We have 2 over pi, 2 over 3 pi. This is for positive n. This is for negative n. Okay, this is for positive n, and this is for negative n. If we refer to signal number 5, okay, so we have these terms here. Yeah, we have these terms here, where we have x naught over pi, yeah, x naught over pi as the c naught value, and for the Cn we have a negative x naught over pi of n squared minus 1, yeah, n squared minus 1. Okay, so for this, we are then given that the Cn value will be 0 for n odd, yeah, for n odd, except for C1 and C negative 1. Okay, so if we base on this, we know that if we put n equals to 2, for instance, n equals to 2, okay, going to have down here should be, let me see, yeah, let me see, sorry for that. Okay, I think I made a mistake now. It shouldn't be number 5. It should be signal number 4, supposedly. Yeah, I think it should be signal number 4. Okay, because for signal number 4, there is no comment here. Yeah, so we can use signal number 4, in which by putting x naught equals to 1, yeah, by selecting x naught equals to 1, and we are now trying to substitute n equals to 1 and n equals to 2. So yeah, 1 and 2. Okay, for x naught equals to 1, we know that your amplitude will be equals to, the c naught shall be equals to 2 over pi. Okay, here should be a negative 2 over pi for n squared minus 1. And if we're having n equals to 1, so it should be negative 2 over 3 pi for both n equals to negative 1 and positive 1. And if we have n equals to 2, we are supposed to get negative 2 over 15 pi, correct? Negative 2 over 15 pi for both n of negative 1 and n equals to positive 1. So I believe that for this example, the solutions, the given function of ft here is related to signal number 4. Signal number 4, okay? Okay, so you can substitute the value of x naught. You can choose x naught equals to 1. And by substituting n equals to positive 1, negative 1, you're going to have 3 pi. By substituting n equals to positive 2 and negative 2, you're going to have 15 pi for this n equals to 2 and n equals to negative 2. Okay, is it understood on the solutions number 1? It is related to number 4. Okay, I repeat again. We can see that the signals that we are given here, this equations here, is related to signals number 4, in which we can substitute the value of x naught equals to 1. Yeah, it's not 2. So it can be agreed now that ft is a full wave rectified signal. Okay then. Is there any question for question number 1 for part 1 of the questions? I think I made a mistake for the solution. Sorry for that. Yeah, it's not signal 5. It should be signal number 4. Yeah, signal number 4. Okay. Let's have a look at this number 2. I mean part 2 of the questions. Part 2 of the question asks us about write the trigonometric equation of signal ft. Okay, so basically we need to be based on this ft. Okay, just a transformation from complex exponential to trigonometric, in which we have done this yesterday. Am I right? Okay, we have done this yesterday, so I think it's nothing much to be worried. So based on these equations from above, we're going to combine the same terms. Yeah, and one thing to be remembered that to be considered is that all the negative 1 here, yeah, negative 1 is written to be, or negative 1 is also equals to exponential j pi or exponential negative j pi. Yeah, okay, negative 1 is equals to exponential j of pi and exponential negative j of pi. You can prove it using the Euler's relationship. Okay, so that's why all the negative sign from ft is now transformed as exponential of j pi. Okay, so we can write it as follows. Okay, we're going to have 2 over pi and 4 over 3 pi. The terms have been changed into the cosine trigonometric for a frequency of 2 and a frequency of 4. So we're going to have ft should be look like this. So from this ft, straight away we can sketch the spectrum. So ft in trigonometric cosine should be a single-sided spectrum. So we should have a spectrum look like this. The amplitude will be 2 over pi for omega equals to 0, DC value. For omega equals to 2, we're going to have 4 over 3 pi. Omega equals to 4, we're going to have 4 over 15 pi. And the same goes for the phase plot. We're going to have for 2, omega 2, we're going to have pi. And omega equals to 4, we're going to have pi also. So that should be a solution for that example. Is that understood then? Hello?
Understood, Doctor.
Okay,
Understood.
thank you very much for your reply. Yeah. Okay then, I'm not sure for this particular Zoom software, we're going to have only another 1 minute, because basically Zoom is limited only for 40 minutes. I'm not sure why. So let's say if we cannot proceed with Zoom, okay, we have to go back to Google Meet after this, yeah. Let me wait for 1 minute, one more minute. If we cannot proceed with Zoom, so we have to go back to Google Meet then, yeah. Okay. Somehow it looks like we have to stop the presentation now. Okay, sorry for this. I think I have to stop the presentation now. Okay, I have to stop now. I'm going to give you a link for Google Meet. Yeah, Google Meet very soon, yeah. Sorry for this problem.
But please, doctor, upload the this lecture.
Yes,
This one,
yes.
like yeah, in the part 2 and the.
Correct. So I'm going to transfer now to Google Meet. So I'm going to give the link very soon. Yeah. So I'm going to stop now. Yeah. Okay. Thank you.